All right, sorry about having to cut my last video a little bit short. My 2-year-old walked into the room and I had to stop and help him out. So we are back to this part where we left off. So what we were doing here was kind of confirming what we said that we wanted to be the case of our velocity vector function, which was that the magnitude of that velocity vector at any given time represents the speed of our particle. And this shows that the velocity or the magnitude of v of t is equal to ds dt, which is what we would expect speed to be, a change in distance. S represents arc length, so that's a distance, over a change in time. Now, we want to talk about acceleration also, and we're going to simply define acceleration as opposed to try to come up with a derivation of it the way that we did with velocity. And we're going to define it exactly the way that you would expect to based on what you know from Calculus 1. Velocity is the derivative of position. We're going to define acceleration to be the derivative of velocity. Okay. Now, as we work with this concept, we're going to explore the acceleration function in more depth towards the end of this section. But what I want to do is connect this to something that you should know from physics, which is Newton's second law of motion. So to make this connection, the first thing we need to do is try to think of this point that's traveling along this curve, the space curve, as an actual object with mass. So we're going to think of that point as having a mass of m. Now, mass is a scalar quantity. It doesn't have any direction, so that it doesn't make sense to assign mass a vector. It would be a scalar. And from Newton's second law of motion, we know that force is equal to mass times acceleration. You have an object in motion. The reason that object is moving is because forces are acting on it, and the net force acting on that object will determine an acceleration, and mass times acceleration will be equal to that force. That's Newton's second law. We use this in Calculus 2 as well. But we've already seen that force in this class is represented by a vector, and we've defined acceleration as a vector as well. And force is not necessarily constant. Force can be a variable function. So when I say here possibly variable force, that means that force can be changing depending on depending on the time t or the position of that point. Force is a vector, acceleration is a vector. What does this actually show us? Well, force is equal to a scalar times acceleration, which means force is a scalar multiple, or our force vector is a scalar multiple of the acceleration vector, which means that the force and the acceleration point in the same direction. And that's kind of one really important thing to consider when we are looking at the acceleration vector at a given time. It's going to be pointing in the direction that the net force is acting on that particle. And now I know a scalar multiple of a vector can be pointing in the opposite direction as well, but that won't be the case here because mass is necessarily a positive quantity. You can't have negative mass. And if you multiply a vector by a positive scalar, you're not going to flip directions. So these do always point the same direction, F and A. Okay, so let's kind of explore this in a little bit more depth. We have an example here where we want to find the velocity, acceleration, and speed of a particle with this given position function right here. This one's straight out of your book in the text. I wanted to use this example because I wanted to use the graphic that came with it to make sense of the acceleration function. So we'll quickly find the three things that it's asking for, starting with velocity. What is the velocity function? Well, again, velocity is just r prime. We differentiate our position function, and that provides us with a velocity function. That would be 2t e to the t. And then I'd be using the product rule here. If you use the product rule and then factor the result, what you're going to end up with is 1 plus t e to the t. Okay, I'm skipping the steps as I'm typically going to do of sort of the Calculus 1 grind of, using the product rule and showing all those steps and everything. There's our velocity function. Let's find an acceleration function next. Acceleration is defined to be the derivative of our velocity function. So I would be taking the derivative of this thing. That would give me 2 e to the t. And then again, I'd use the product rule on this, and then factoring the result gives me this, 2 plus t e to the t. By the way, this is more of a calculus 1 thing than a calculus 3 thing, but you should notice a pattern going from here to here. At this point in your mathematical careers, you may be asking, is there a way to generalize this if I took an nth derivative of this function? And there is, but we're not bothering with that here. Just a little side note worth mentioning. What about the speed of our particle? Remember, speed we're going to denote with a v, but a v as a scalar, not a vector, so I'm not putting an arrow over it. V, which is the same thing as the magnitude of our velocity function, is just the magnitude of this vector function that we already found up here. Okay, so squaring that would be 4t squared plus e to the t squared, or e to the 2t, same thing, plus squaring that last term, 1 plus t squared e to the 2t. That's really fine to just leave it in that form. I'm not worried about simplifying that anymore. Okay, so all three of those things were very straightforward to find because it's just a matter of finding derivatives. Now, this graphic shows up in your book, and it's a part of the space curve given by this function, and this point right here, it corresponds to t equals 1 on our position function. And what they've done is they've, in addition to giving us the space curve, they've graphed the velocity vector at that point as well as the acceleration vector. Now, because the velocity vector comes from r prime, the velocity vector will always be tangent to the space curve at that given point, because that's what r prime is. It's a tangent vector. So velocity is always tangent, and that makes sense because the tangent vector should point in the direction that the particle is moving. But what I want to call attention to is the acceleration vector. Notice how, if you could see this black curve here, the black curve has kind of a concavity, right? It's concave. And the acceleration vector is pointing inward to that curve, meaning kind of it's pointing towards the concave side. It's not out here, it's in here. And that is always going to happen. If we think of this in terms of Newton's second law, this actually makes perfect sense. Suppose this particle is traveling through space, right? And so far it's traveled this distance along our space curve. If we, at this point, if somehow all forces acting on this particle were just to disappear, and the particle were now just moving according to its own momentum, then it would be traveling only in the direction of that tangent vector, of that velocity vector. So again, there's forces acting on this particle to move it through space, but then if all of those forces disappear, the particle with its momentum will just travel in a straight line from there. So why is the particle continuing to make this curve? Well, it must be because there's still force acting on this particle, causing its direction to change and follow this space curve. But if that's the case, which direction should that net force be pointing? Well, if the tendency of the point is to travel in the direction of that tangent vector v, then we need a force that's acting in a direction, similar to the direction that the point is going to ultimately travel in. So notice that the curve is kind of between our tangent vector here, v, and our acceleration vector, v, because a force is acting here, kind of nudging the point that direction, okay? I don't know if I explained that very well, but that's where we think of this in terms of Newton's second law. So the force and the acceleration both point the same direction. Knowing that acceleration points this direction means the force acting on this particle, the net force, is pointing in that direction as well, causing the point to follow a curve as opposed to a straight line. Okay? And based on that logic, the acceleration function, we can see, will always point into a curve, never out of a curve. So hopefully that gives you a little bit of intuition. We're going to break that down even more meticulously later on, that whole acceleration vector thing. Let's try this in a different direction. This time, we're going to be given an acceleration function for a moving particle, but we want velocity and position from that. And we're also given a little bit more information. We're given initial velocity and initial position. That's what v of 0 and r of 0 would represent. The velocity at time 0 is the initial velocity, and similar for position. So we know from our work in Calculus 1, again, if you want to do this in reverse, if you want to recover a velocity function knowing an acceleration function, you're doing the opposite of taking a derivative. You're taking an antiderivative or an indefinite integral. So, for example, if I want velocity, velocity should be the indefinite integral of a of t dt. That only makes sense, so that the derivative of velocity then would be acceleration. With that in mind, what is v of t going to be? Well, v of t, if I take the integral of sine of t, that's negative cosine of t I. Antiderivative here is going to be plus 2 sine of t j. Antiderivative of 6t would be plus 3t squared k. Okay? Now, that's not the whole thing, is it? Because we've said when we've done indefinite integrals for vector functions, we also have to take into account that constant vector of integration. And remember, it's a vector. It's not a constant, just scalar value. We're not done until we determine what this is, this constant vector, and work it into our velocity function. That's where we use the initial velocity. So v of 0, I can plug 0 into this. First of all, we know that v of 0 is equal to negative k. That's equal to v of 0. But what if I were to actually plug 0 in to what I have here? Well, cosine of 0, negative cosine of 0, sorry, should be 1. So this is, or negative 1. So this becomes negative I here. And then, let's see, what else do we have? The sine of 0 is 0, so the j term is going to go away. And k is, 3t squared. If I plug a 0 in, that goes to 0 as well. So the only thing I get, aside from that constant of integration, is the negative I there. So plus c. Okay? Solving this for the constant vector c shows me that c is equal to I minus k. All right? So that is what's being added here. C becomes I minus k, or 1i minus 1k, and I can combine those with the I and k components that are already there. So let's rewrite our velocity function with that in mind. Negative cosine of ti plus another I from our constant of integration. I can write that as 1 minus cosine of ti. There's no j being contributed by our constant here, so our constant vector, so that's not going to change. It's going to still be plus 2 sine of t j. And then here we have a negative k that's being added to this, so I can write this as plus 3t squared minus 1 k. All right, so that's the reason we need to have this initial velocity. If you've taken a course in differential equations, or even if you remember doing, a little bit with differential equations in Calculus 2, these values here should look kind of familiar. These are like initial conditions, and they kind of serve the same purpose here. So we're part of the way there. We have our velocity function. Now we need a position function. And again, same idea. Position would be the antiderivative of velocity. So r of t will equal the indefinite integral or antiderivative of v of t dt. And I have v of t right here, so I'm going to take the antiderivative. That would be t minus sine of t I. And then here we're going to have minus 2 cosine of t j plus t cubed minus t k. All right. But remember, we're not done because we still need that constant of integration. Let me call it d this time to make it different. So again, that constant is a constant vector, and we once again need to use what we know. The initial velocity, or sorry, initial position of our particle is given here, j minus 4k. So I can say j minus 4k, which we're given is equal to r of 0. R of 0 I can find explicitly by plugging 0 into what we just found for our r of t function. What would that be here? That would be 0i, so I'm not going to write that. Negative 2 times 1 would be negative 2, negative 2j. And then if I plug 0 in here, that whole thing goes to 0, and then I have my plus d right here. And so we're solving for the constant d just by adding 2j to both sides. That gives me 3j minus 4k. All right, almost there. I just need to take this expression, this constant vector here, substitute it in for the d here, and then combine those j and k components with the j and k components here. So that tells me that r of t, putting everything together now, should look like t minus sine of ti. Negative 2 cosine of t is going to be added to a 3, so let's write that as plus 3 minus 2 cosine of t j, and then my k component is negative 4k plus t cubed minus t. Let's write that this way, plus t cubed minus t minus 4. It should be a minus k, and that's my position function. All right, so kind of both directions there. You can see that in the case of starting with a position function, because we're just taking derivatives, we don't need any initial values. We don't need, v of 0 or a of 0 or anything like that. But if we're going the other direction, starting from acceleration and trying to find velocity and position from that, then we do need those initial values because we're going to end up with those constant vectors of integration. We need to do something with those. Cool. All right. Moving along, let's talk about something that you've definitely encountered at some point, whether in a physics class or even in pre-calculus and trigonometry. We deal with these types of problems. This is a projectile motion, and we're going to think of this just in the context of vector functions. So the idea here, we're going to start by thinking of a projectile that's fired from ground level. So it's fired from the horizontal. And this v naught here is going to represent the initial velocity vector. So you can think of something being fired from a cannon or a baseball bat hitting a baseball and sending it this direction. We're going to assume that that velocity vector, that initial velocity vector, makes an angle of alpha with the horizontal. And we know that projectiles follow parabolic arcs generally, because even though the projectile is traveling this direction, there are forces acting on that projectile as time passes, namely gravity, acceleration due to gravity. That's the force that we need to consider, or force due to gravity. There's also air resistance, but we're going to neglect air resistance here just to keep things simple. So if the only force acting on this projectile after it's sent into the air is gravity, and we know that the acceleration due to gravity, which we always denote by lowercase g, is 9.8 meters per second squared, approximately, or if we're using imperial units, it's approximately 32 feet per second squared, then it would make sense that the acceleration function is negative kj. Why is that the case? Well, again, if acceleration is acting completely downward, because remember, acceleration is pointing in the same direction as our force, and the only force is gravity, which acts downward toward the center of the Earth. That vector right there is a scalar multiple of the standard unit vector j, the standard basis vector j, and it has to be a negative scalar because it's pointing down. Finally, we know that the magnitude of that vector should be g, so negative g, j, that's where that's coming from. Once we have that acceleration function, we can kind of do what we did in the previous example to come up with velocity and position functions. So starting with velocity, if I were to integrate my acceleration function, that would give me velocity, and that results in negative GTJ plus some constant vector c. And before we go any further, we want to determine what that constant vector is. So remember, if I were to plug a 0 in for t, v of 0, that should be giving me my initial velocity vector, which were shown here. I'm not working with any specific constants, any specific values, so I need to keep things kind of general. And in order to determine what that constant vector looks like, we need to decompose this vector into orthogonal components. So what that means is take our velocity vector v and break it down into a vector pointing in the direction of our unit vector I and our unit vector j. So let me call that A, I, B, J. Okay? But knowing this angle is what makes this possible, because with a little basic trigonometry, I can find the magnitudes of these vectors, which is what A and B would represent. A is going to equal the magnitude of V naught, which remember we're going to use V naught without the arrow notation to indicate the magnitude of that vector, times cosine of alpha. B is going to equal V naught times sine of alpha. That would be the length of those legs of that right triangle right there. So putting these into our vector function, the velocity, our initial velocity, we can see that this initial velocity vector is just the sum of these two vectors. Notice we're adding them tip to tail right there. So that means V naught, or V of 0, is equal to V naught cosine alpha I plus V naught sine of alpha j. All right, this is the constant here. So I'm going to substitute this entire expression for that constant here, and notice I have a j component and another j component that should be combined, giving me this. V of t, after simplifying, is V naught cosine of alpha I plus V naught sine of alpha minus that gt j. All right, so we're headed the right direction. What we really want, though, is a position function. So position, that's r of t. I can find that by integrating what we just found, my velocity function. And integrating this, again, don't be too thrown by this expression. That whole thing is a constant right there. We're integrating with respect to t, and there are no t's there. So integrating this is just going to give me V naught cosine of alpha t. That's my I component. This guy, that's a constant, and this second term here does have a t in it. It integrates to V naught sine of alpha t minus 1/2 gt squared. That would be the antiderivative of this. But again, we end up with another constant vector of integration. So I need to determine what that constant vector is so that I can include that in my r of t function. Now notice if I plug 0 in for r, the t here, the t here, and the t here, it causes everything to go to 0. So r of 0 would just be equal to that constant vector. But now we have to think of what r of 0 is in the context of the original problem. Remember, that's the position of the projectile at time 0, or the initial position. And if you look at how we set up our coordinate axes here, the initial position is at the origin, right? So r of 0 would have to be the 0 vector, because that's the position vector for the origin. So that's kind of convenient, because that means that this constant vector d is just the 0 vector, which means it doesn't even contribute anything. I can just get rid of it, and whatever remains becomes my position function. Now, this is somewhat of a special case of a more general position function, because who's to say that in a particular problem we would want the projectile to be launching from ground level? Oftentimes, the projectile is going to be launching from some height, say h, right? So if the projectile is going that direction, and it starts from height h, then using this right here, the initial position is our constant of integration. Or specifically, the initial position vector is that constant vector. And in this case, I can see that that position vector would be h, which is a scalar, j, because that vector is pointing in the direction of j. So that means I have to add hj here, which if I do that and combine that with my j component that's already there, I just pick up an extra plus h in that j component. So this is kind of the more general position function for this projectile. That little h there is the only difference. Okay, and you can see that if we're starting at ground level, h would be 0, and this would reduce to this. All right. So I'm looking at our time. I think I'll start this next example in the next video.